So guys, last week, right, lesson before this, we saw how benzenes react with electrophiles, right? So I'm gonna go back to basics again, very quickly, we'll just recap. So Yap Chen, I want you to tell me, right, if you look at this benzene here, so come, can you tell me, are benzenes nucleophilic or electrophilic?
Nucleophilic, because of the pi electron cloud above and below the ring.
Okay, so we have how many pi electrons, remind me?
2, 4, 6.
Very good, 2, 4, 6. So guys, you can see that he was counting, right? So the reason why he was counting is because benzenes look like this. Of course, we draw a circle. So we know that there are pi or p orbitals everywhere. And like what he just counted, you have 6. Now guys, I'm not sure whether this was mentioned in class. You might have forgotten. If you have, it's fine. I want you guys to compare between the strength of nucleophiles between benzene and alkene. So benzene, we have 6 pi electrons, and alkene, you have 2. So we just established that both nucleophiles. So Yap Chen, who do you think is a stronger nucleophile? 6 pi electrons benzene or 2 pi electrons alkene?
Well, I mean 6 is more than 2, right?
Of course.
So should be the benzene, right?
Exactly. Now here's the thing, right? It should be the benzene. So, but if benzene is a stronger nucleophile than alkene, then benzene, for you to react with your chlorine, it needs a catalyst, right?
Oh yeah.
Yeah. But alkene doesn't need a catalyst.
No, room temperature is fine.
Exactly. We do it at room temp, CCl4, if you can recall, right, in the dark. So this tells you something. The fact that benzene requires a catalyst to react with the ClCl, benzene must be a weaker or stronger nucleophile.
I mean, if you need a catalyst, that means it must be a weaker nucleophile.
Of course. Exactly. So benzene, it has to be a weaker nucleophile compared to an alkene. Very, very weird, right? Very counterintuitive.
Yeah, I mean like 6 is more than 2, right?
Yes, I think so. So can you shed some light? Why do you think? Make a guess. Make an intelligent guess.
I mean, the difference between a benzene and an alkene is resonance, right?
Fantastic.
So it must be due to resonance.
Okay, so benzene is resonance stabilized, guys, right? So because it's resonance stabilized, do you think you want to give up 2 electrons to attack?
No.
No, because the moment you do that, are you still resonance stable?
No.
No, you're not. So benzene is very, very reluctant to do this. So here's the thing, okay, guys. Now, this ClCl, we know that it is a weak electrophile. Can you shed some light, Yap Chen? Why is this a weak electrophile?
Well, this ClCl is a non-polar molecule,
okay,
right? So you only have a partial charge when the electron-rich species approaches the ClCl, repelling the electron density to one side, giving rise to a partial positive on the other side.
Perfect, yes. So your chlorine, before the nucleophile comes in, do you agree, Yap Chen? The electron cloud looks like this?
Yeah, symmetrical.
Very good. And when the nucleophile approaches, what happens?
I mean, the electron density will be repelled to the right side.
Exactly. It looks like this. Now, so what charges do we use, Yap Chen? Do we use a negative like this?
No.
What do we use?
The D.
Yes, we use the D.
What did he say?
The delta negative and delta plus.
Yep.
Okay, now this delta, or the D, is this partial, is this a very big plus charge or very small plus charge?
I mean, you already said it's partial, so I mean, it should be less than
It should
1.
be, yeah, exactly. It should be less than 1. It's quite a small plus charge, so that's why it is a weak electrophile. So, Yap Chen, so do you think a weak nucleophile can react with a weak electrophile?
I mean, 2 weak, I don't think it will work, right?
Yeah, 2 weak people, they can't. If you take 2 weak people and they fight, the outcome not going to be very great. You won't know who wins, right? Not very clear. So we need to convert this weak electrophile into a stronger electrophile. And how do we do that, Yap Chen?
We will use the halogen carrier catalyst.
Excellent, yes. We use a halogen carrier catalyst. Can you remember what it was?
AlCl3.
Okay, AlCl3. Now, I'm going to write this down here with you guys. Let me clean things up a bit. Halogen carrier catalyst. Now, as the name implies, right, Yap Chen? What does halogen carrier catalyst mean?
Catalyst.
Okay, yep, it's a catalyst,
Yeah,
yes.
right.
Killing me right here. Yes, but it carries away the...
Halogen.
Exactly, right? So halogen carrier means it carries away the halogen. So you're going to do this with me, okay, Yap Chen? We're going to take this catalyst and we're going to do this. We're going to carry away this halogen and we're going to pull it out. Just like this, pull it out. Now, when you pull it out, this becomes AlCl4 minus. Now, because before this you were neutral, right? Cl2, AlCl3, completely neutral.
Yeah.
So to make sure charge is conserved, if this becomes AlCl4 minus, this must become?
Cl plus.
Yes, very good. This must become Cl plus, and hence you're still neutral at the end.
Yeah.
Very good. So with this here, are you still a weak electrophile or strong electrophile? Let me clean things up.
I mean, with a full positive charge, it will be a stronger electrophile, right?
Yes. So what we have just done, in the presence of a halogen carrier catalyst, we just converted a weak electrophile into now what we have a strong one. So do you think this reaction works now, Yap Chen, with benzene? Of course it works. And of course, I will cut straight to the point. We will get this. Okay, I won't show you mechanism here. I hope you guys can recall. If you forgot, you can flip back to your notes. Okay guys? So now, Yap Chen, I'm going to throw you a curveball. Now, instead of chlorine chlorine, right? What's so boring? Now we have bromine chlorine, okay? And of course, I'm going to take benzene. I'm going to try to react it with bromine chlorine in the presence of a halogen carrier catalyst.
Okay.
Yep, Chen, this is where I want you to think with me. This halogen carrier catalyst, now he's in a bit of a sticky situation. He can either take away this chlorine, okay? And if he does that, you get this. Oops, excuse me, guys. You get this. Or if he takes away the bromine, and I'll do this in red, if he grabs the bromine instead, you will get this. Now, Yap Chen, I want you to think, which do you think is more preferred? The blue one or the red one?
Well, I mean, bromine is less electronegative than chlorine, right?
Okay.
So, if we were to bear a positive charge, I think bromine would be the preferred one to bear the positive charge.
What does electronegative mean again? I forgot.
I mean, electronegativity refers to the ability to attract shared pairs of electrons to yourself, right? So if you are less electronegative, you'll be less willing to attract electrons to yourself. So that's why the bromine will bear the positive charge.
Makes sense, makes perfect sense. Yeah. Okay, so bromine is less electronegative, so it wants to bear the plus charge. So we would prefer the blue one, right?
Yeah.
And that's where benzene attacks this, and of course, everything as usual. We end up, of course, in a mechanism you can draw on your own again, you will get this.
Yep.
Yeah? Cool. Okay, so now a bit more of a curveball, a bit more difficult now. What I'm gonna do here for you today is this, something a bit different. I'm gonna step you outside of your comfort zone and we're gonna see this. So benzene, I'm gonna try to generate methyl benzene. Okay, so guys, methyl benzene. Now, so come, I want you to back postulate with me and think a bit.
Okay.
If I want to generate this methyl benzene, what strong electrophile do I first need?
I mean, drawing parallel from the previous example,
Okay.
if you want to insert a chlorine, the chlorine must have the positive charge. So if you want to put in a methyl group, you have to have a CH3 with a plus charge.
Makes sense. So CH3.
Making sense.
Yes, yes. Do I put a plus charge on the hydrogen or the carbon, Yap Chen?
Carbon.
Why not the H?
Because the bond is to the C, right?
That's fantastic. Yes, exactly that. Guys, please notice this is a huge mistake, okay? The benzene is bonded to the carbon, not the H. So the plus charge must be on the carbon because at the end of the day, the benzene must attack the carbon, not the H. Okay, and hence we form a bond. Cool. Let's backtrack a bit more, Yap Chen. So how do I form that plus charge on that carbon?
Oh, that's
A bit more difficult.
That's a bit tricky. So you probably have to join it to something more electronegative because based on the BRCR example,
Okay.
right, the less electronegative one will adopt the positive charge, right?
Okay.
So the carbon has to be joined to a more electronegative element.
Okay, so give me an example. Okay,
Chlorine?
Okay, chlorine. So backtrack. To generate this CH3+, maybe I'll attach a chlorine to this carbon. And what Yap Chen just said is exactly right. Carbon is less electronegative, so it would want to bear the plus charge. If I put a halogen carrier catalyst here, it would prefer to carry away the chlorine and leaving the plus on the carbon here. Okay? An easier way to also see it is because, of course, right, we call it a halogen carrier. We carry away halogen, not carbon. That's a faster way to see it as well. Alright, so up to you guys. So once you have this, you will get AlCl4- and CH3+. And of course, once you have this, you have the CH3+ generated, the strong electrophile, and that is where benzene comes in to attack this to give us our beautiful methyl benzene. And that's it. Okay? Cool.
I have a question.
Yes, what's up?
What's the name given to this reaction again?
Electrophil, what's the, come, let's think about this. So you're asking me for the name of the mechanism, right?
Yeah.
Yeah? So I'm gonna guide you through this, okay? And guys, please listen, and listen up close. Remind me again, Yap Chen, is this electrophile or nucleophile?
Electrophile.
Electrophile. And there was once a hydrogen here, correct?
Yeah.
Yeah, there was once a hydrogen here. Any more hydrogen here?
No.
No, right? So what did we just do? We took an electrophile and we substituted away the H.
Right.
Agree?
Right.
So what do you, I'm going to throw the question back to you. What do you think this mechanism is called?
It will be a substitution reaction
Be more specific.
involving an electrophile, so
Okay.
it should be called electrophilic substitution.
Electrophilic substitution. Very good. Okay, so yes, we just saw how this acylation works, right? You just put in an acyl group. Alright, cool.
I have a question.
Yeah, what's up?
So what's the name given to this reaction?
The name of the reaction, or this is what we call Friedel-Crafts. Okay, I would take a step back. We call it alkylation because we're putting in an alkyl group.
Okay.
Okay. And then we're gonna, of course, attribute it to the scientist's name. And the two scientists, they are called Friedel-Crafts. So Friedel-Crafts alkylation. Good question.
Not art and craft.
Moving on. Okay, yeah, Friedel-Crafts alkylation. Now, when you guys go for class today, and I think again, you guys, some of you are watching this on the bus, on the way home, whatever it is. What you're going to see in class today is this. Your teacher is going to teach you this, okay? And I'm going to leave this to your teacher. He's going to show you how to put in an acyl group. Now notice my pronunciation, not alkyl. Acyl, the C, okay? And this is how an acyl group looks like. Alright? And I'm going to let your teacher bring you in and teach you the rest of this. Alright? That's it, guys. Okay. See you in class. Bye-bye.
Bye.